Oh, yeah, because I put you in manually.
Oh, okay.
Yeah.
Gotcha.
Okay. Are you like at school now?
I'm visiting my boyfriend in Boston and we're like on the BU campus right now.
Oh, cool.
Yeah. Hmm?
Is it snowing there?
Um, I think it's supposed to start soon,
Got it.
but I'm driving home after this, so I'm hoping that it's not going to start
Yeah.
until later.
Yeah, it's snowing where I am right now.
Oh, okay.
All right. So, yeah, good job on this test. And you were saying about CP that you like were always having a problem with CP?
Well, I mean, I've been having an issue with CP for a while because I feel like my scores have been the same this whole time, and I haven't really seen any improvement.
Got it.
And specifically on this test,
Hmm.
I ran out of time for the end questions. Like, I think there was like four or five questions that I didn't even really get to see. Like, I read the question really quickly and then just kind of chose an answer to finish on time. But I'm not really sure why because like I was looking at my like the questions and how long I took. And I didn't even realize like I was taking that long. So like I think there was one question that I spent like 7 minutes on,
Uh-huh.
which is just crazy. So
Yeah, yeah.
um I'm not sure like why there's been so many
Mhm.
like I'm looking at them now. But I think like all of the questions that I spent like a really long time on were like 4 minutes, 4.5 minutes.
Yep.
Um,
So,
yeah,
yeah, let's look at the types of questions that you're either getting wrong or spending too much time on. Like we could see if they're like calculation problems or if they are, yeah.
yeah, I definitely know that the calculation problems take me a while because it takes me a while to even,
Hmm.
I guess, wrap my head around what I'm supposed to be doing. And then once I finally do that, I have issues with like dimensional analysis still. So,
So, all right. So, yeah, let's go over some of that stuff.
um, I don't know if it would be helpful maybe to like do a whole new passage because I think my analysis of the passage also needs some work too.
Mhm.
Or if you think it would be better to go through ones that I've already done.
Uh, let's start by just looking at the types of questions in CP that
Okay.
you are either getting wrong or spending a lot of time on, just so we can get a, a good idea of yeah, like what type of questions for the most
Okay.
um and uh and definitely like, some I'll show you some like ways to do the math.
Okay. And let me just pull up the test.
Mhm. What was the name of like the spreadsheet that you made
Um,
to like keep track of
it's
your
just called practice questions.
got it.
And then this one would be CP Orgo all the way at the bottom.
Okay.
Okay, the first one I spent a long time on.
Mhm.
I also was reading the passage during that time, but I think I was having an issue, uh, I guess, figuring out whether or not HIV protease is a good thing or a bad thing. Like, would you want to inhibit
All right.
it? Like, So that's like more of a conceptual, I
Yep.
think.
Sure, you could share your screen.
Oh yeah. One
Mhm.
second. Okay.
Okay, um, so let's have you like read the passage and identify buzzwords. So yeah, go for it.
Okay. HIV protease is an example of an aspartyl protease. So I'd probably highlight the fact that it's a protease.
Yeah, what would
Um, it breaks down proteins or like cleaves the bonds
what type
in
of bond
protein peptide bonds.
and what a functional group is a peptide bond?
Um, it's a cysteine, right? Or no, that's disulfide.
So,
Um, would that be like between the carbonyl and the amine
yep. So what
group?
functional group is that called?
Um, like the carboxylic acid.
Uh, so the carboxylic acid that, well, here, a carbonyl attached to amine.
Oh, is that an amide?
Yes.
Okay,
And amides are particularly stable because there's partial double bond character.
okay.
Right. So you want to know all of the bonds in biomolecules by not just their name, like peptide bond or glycosidic bond, but also the functional group for them.
Mm-hmm.
So, okay, so a protease breaks proteins at the peptide bond, right? And that would be through hydrolysis, right? So, okay. And they're saying this is an aspartyl protease, which particularly cleaves, um, well, wait, utilizes an aspartate side chain during the catalytic cleavage of a peptide bond. Um, okay. So I guess it says that it uses an aspartate side chain, but
But I mean, not to get ahead, but
Mhm,
in the amino group or amino acid, like, isn't it between
mhm.
phenylalanine and proline?
Yeah. So yeah. So at first I was thinking it would break the peptide bonds of aspartic acid, but it says that it utilizes an aspartate side chain during its cleavage of the peptide bond. So it's just going to be using that to help it, do what it does.
Okay.
So now they're saying since HIV protease is a relatively small homodimer of a 99 residue protein, so right away, what, you know, would be thinking here?
Well, that it's a homodimer,
Okay.
so
That means,
it's two different like peptides that are the same but put together.
oh, okay. He said two different that are the same, but you mean,
Oh, I
okay.
didn't mean like two peptides that are the same that came together to
So,
form one.
so there's a quaternary structure here, right?
Yeah.
Okay. And when they give you something like 99 residue protein, what did they ask you?
Probably to calculate the weight.
Uh-huh. And you would be using what, like,
110 Daltons
mhm,
for um protein or
per
amino
amino
acid.
acid. Good. It can be directly synthesized or cloned and expressed in fast-growing cells. So the cloned and expressed in fast-growing cells would be like if you insert it into like a, you know, a plasmid in a bacteria, and the bacteria reproduces through binary fission.
Hmm.
Okay, for this reason, it was targeted for structure-based drug design in order to treat HIV infection. So this HIV protease, was targeted to treat HIV. Now, a portion of the peptide cleaved by HIV protease is shown in figure 1, and we see like phenylalanine here. We see, I'm not sure what this one is. See, it's like another amide that it's bound to over here. Um, Another phenylalanine, a proline, a
I think that's
huh,
forget. With an amide, is that like arginine?
possibly.
I think
Okay.
maybe.
Have some like non important one there. So okay, whatever. So we see those, and yeah, that's what you'll do. Like whenever you see structures like this, you identify functional groups. All right, and then they're saying using molecular models of the HIV protease enzyme, researchers designed and synthesized transition state analogs. One such molecule is compound 1, shown in figure 2, which is a potent HIV protease inhibitor. So we see it here. We see there's lots of rings, heterocyclic rings, which is, involve rings with things other than purely carbon, like nitrogen and stuff. And
Hmm.
yeah, okay. So now if they designed a protease inhibitor for a treatment, is HIV protease like good or bad?
It's um bad.
Bad, right?
Yeah.
Good. Okay. Then it says compound 1 has an in vivo half-life of 1.8 hours and is primarily metabolized by CYP3A, an enzyme in the cytochrome 450 family. The major metabolite of compound 1 results from the dealkylation of CH2R groups attached to the pyrazine ring system. Reaction 1. So reaction 1, we have compound 1 through the CYP3A. Seems like it gets cleaved um, over here,
Hmm.
and like, yes, here, right? Okay.
Yeah.
One of the main side effects of prolonged compound use of compound 1 is the formation of kidney stones composed of calcium oxalate. We have that there. Researchers use their knowledge of the HIV protease active site and the metabolic pathways that lead to destruction of compound 1 to design and synthesize several derivatives of compound 1 in an effort to modify its properties and increase its potency and half-life. So this compound 1 is an example of this protease inhibitor, right?
Hmm.
Okay. So so when you first read it, like, did you get like
I got some of what we talked about.
got it?
I think when I was reading through it, I kind of skipped over the dealkylation.
Okay.
Um, and also like one of the issues I had, which goes into question one, is determining whether the protease was like something you wanted or something they didn't want.
Okay.
Um, yeah.
So now you would see that where in the passage that
In this paragraph, talking about um the compound that they're designing is an inhibitor of HIV protease.
correct. So if we look at these choices, let's hide the solution so we can see each of them.
How do you hide
Select just press this button here.
the gray one?
This one,
Oh,
that
yeah.
one works too.
Okay.
Okay, so we have an agonist which works for it, an antagonist that works against it, placebo that doesn't really do anything, and then we have a catalyst which is just, an enzyme or something that, you know, speeds up a reaction. So, you were probably able to eliminate C and D, and
Yeah.
yeah, now you know that it'll be the antagonist, right?
Mm-hmm.
Okay.
Um, okay, then
Oh, there's not no other questions for this.
I'm just looking to see if um I had more questions on this passage.
Seems like
Um,
stereoisomers.
yeah, I just didn't know, like I thought the equation was, yeah, I thought it was 2 to the n plus 1, but it's 2 to the n.
Plus one.
Yeah, and I think that's for something else, like half-life or something. I don't remember where I saw that.
Okay, okay. Yeah.
Yeah, so I just got it wrong because of that.
So
Um,
if you kind of think about like how that even comes to be, you could just think about, for instance, if I just had, let's say, so any chiral carbon can be determined by wedges, and
mhm,
so a chiral carbon must be bound to four different things, right?
yeah.
So, but at each chiral carbon, like this one, there's only two possibilities. There's this and there's this, right?
Hmm.
So that's where the two comes from, right? So now if
Yeah.
we add both of these, like another one with the wedges, that would be another two possibilities, right? So for
Yeah.
chiral carbon, right, there's two possible like configurations.
Hmm.
And so if n is the number of the chiral carbons and each chiral carbon has two like forms, that's where the 2 to the n power comes from.
Got it.
Right? So helps a lot always to understand like the why of things, and when it comes to equations and stuff, to also understand like how we even come to that equation without, rather than just like if you just memorize it, then if you memorize it
Hmm.
correctly, then it's not going to help.
Yeah. I think out of context again, like that is an example of like I would have understood it, but then when I was being timed, I started forgetting everything that I knew.
Yeah, yeah. So okay, okay. So um got it. Okay, let's see what's the next one. The solubility on
Um,
a constant.
oh yeah, that one. I was just a little bit confused. I mean, I got it right, but I was confused, I guess, because if the reactants or not the reactants, but the like the ions that it dissolved into were higher, then doesn't that mean that the precipitate like wouldn't form?
So the KSP value represents the maximum concentration at which something can remain soluble. So if we are being asked, about kidney stones, which happens when it's a concentration so large it's no longer soluble, then it
Hmm.
would make sense that it would be larger than the KSP, right?
Yeah. I think I
Yep.
just got confused because I would have thought that the um where did it actually the like calcium oxalate would be the thing that should be higher than the KSP because then there's more of the thing that actually forms the kidney stones.
So
That
this
was my thought process.
so this would be a solid, right?
Yeah. So wouldn't that form the kidney stone?
Well, that would be so like the kidney stone itself is that, and it's a solid, but we don't include, solids, liquids, pure substances and stuff into our K expressions, right?
Yeah.
So that's why KSP, like, never has a denominator because the like anything with capital K is from the law of mass action, which is product concentration over reactant concentration. But you never include like liquids or solids. So the calcium oxalate is a solid, and that is not included in the KSP equation. So we're not including it. But if you just think of it conceptually, um, KSP represents the value, the maximum concentration at which this would remain soluble. So if it's beyond the KSP, then it's no longer soluble.
Hmm. Okay. And then the next one, oh, this one I would have like I when I did my blind review, I got this one right. But when I was timed, it was really difficult for me to kind of like I guess see like just visualize. Um, because like I missed the proline here and like didn't see that it was proline, you know. I kind of like skipped over that.
Um, do we even have an alanine here?
Um, no, but I saw alanine as like just the dash.
Okay.
Like I just like I don't know.
Sure. So, yeah, it seems like you spent 31 seconds on this, which is, probably why, but uh yeah, proline is unique in that, it not only has a ring because there's other amino acids with rings, like phenylalanine, right? But
Hmm.
proline is the only one where the ring is bound to the backbone, peptide backbone itself. So it gives you a secondary amine,
Yeah.
right? Because this
Um,
amine here is attached to two carbons through that ring.
yeah, I think if they weren't showing the chirality of the molecule, I would have gotten it right. But
Uh,
as soon as they introduced the fact that it was in a dash, I
mhm,
guess I didn't see that it was even a ring.
mhm. Got it, got it. Yeah. So yeah, be careful with that and just get into the habit of whenever you see a molecule's structure, spend a couple of seconds to identify functional groups and like because when I was first reading this over here, that's what I did. I was like, okay, phenylalanine. Um,
Mhm.
I completely forgot what this would be, and phenylalanine again, and then this one would have to be like at the very least not alanine.
Mhm.
Other one like this one that I'm not certain of, and then this is some isolute like some unimportant, nonpolar one. And
Yeah.
and yeah, that way you get to see that there's no like even if I didn't know what these were, I know that there's no alanine here, and I know that what's relevant to the proteolytic cleavage site is the phenylalanine and this thing.
Mhm.
So let me see so like hit solution again. Let me see just the other choices. So we would get rid of anything without the phenol, right?
Yeah, and that's what left me between alanine and proline, and I saw the wrong one.
Yeah. And what does alanine look like?
It's just a methyl group
Uh-huh.
coming off of it.
As its side chain, right? So after
Yeah.
glycine, it's like the least, it's like the smallest, most simplest one, right?
Hmm.
So yeah, okay.
Um, Next one I spent 2.5 minutes on, but it was a new passage.
Uh-huh. But oh,
Um,
got it.
I'm just seeing oh, I don't think I had an issue. The next one that I flagged was um number 9, which
What that
what
this one with the math question was that?
this one?
Oh, you got it. Right or
Yeah, I got it correct.
okay.
Um,
So oh, okay. So you want to do this?
this one
Mhm.
I just didn't put two and two together that electric potential is voltage. So I was confused why they were talking about potential.
Got it. So what is voltage exactly?
Um,
Oh, can you hide the solutions again?
yeah. It's the electric potential, I guess, for between two plates. If you're talking about it in terms of like a capacitor.
Just okay, so this is just two plates with an electric field between them, and the electric field lines are going from left to right, which indicates what?
Um,
Uh-huh.
it indicates that the plate on the left is positive and the plate on the right is negative.
Okay. So now let's say we have positive charge here. So let's say here. And let's say you are pushing this positive charge against this electric field some distance here, let's say from A to B.
Hmm.
So the work you must do, um, the work you must do, um, in pushing this positive charge from point A to point B against its electric field could be the joules of work per coulomb of charge is your voltage. So you could see that it's voltage is essentially like energy over like energy per coulomb.
Mm-hmm.
And that's where the word potential comes from because potential, we think of potential energy, right? So cell potential, that's what they mean. They just mean essentially energy when they talk about voltage. It's just energy per coulomb.
Okay.
So if you picture it this way, then it could help make you understand exactly what potential means, or rather, that potential it means voltage and what voltage actually means. Now, um, okay, so now what are these two things?
Um, well, resistivity is based off of like how much resistance an electron
Wait, what?
has, like how much resistance an electron has, like as it's moving.
Huh? So if we think about regular resistance in a circuit, it's going to be equal to resistivity, which is represented by rho,
Mm-hmm.
times length over area.
Mm-hmm.
Okay. And I don't know if I went over this with you before, but I did I draw like the cross section of like a wire
No,
and how electrons brush against the copper atoms?
no.
Oh, okay. So that's why. So cross section of a wire composed of various copper atoms and electrons that flow through. That's cross section. Now, this is a side view where, again, we have just a bunch of copper atoms and our electron travels across this and it brushes up against these copper atoms as like kind of like friction.
Mm-hmm.
And like friction, it means that energy becomes lost through heat. And that's what resistance is. So now if we imagine elongating this, we need, which means more and more of these copper atoms. What would happen to, would these electrons brush up against these atoms, copper atoms, even more or less or the same?
Um, I mean, adding adding more of a length to it would increase the resistance, but like because it's the same medium, it wouldn't like brush up more in one section over another.
Like, let's say that you're the electron and the copper atoms are like a crowd.
Mm-hmm.
And, let's say this is the length of this tunnel or something. And you brush against, let's say, two copper atoms here. But if we lengthen this, you'll brush up against even more, right?
Yeah.
So it should make sense that as length increases, resistance should increase, right?
Mm-hmm.
Now, alternatively, if this cross section of this wire was significantly larger, the electrons can travel through more of these pathways, right? It can kind of go through like, here and stuff.
Yeah.
So it could enable it to brush up against fewer copper atoms, right?
Mm-hmm.
So, oh yeah, for the side view, it would be more like if I did something like this, if it's this much thicker, right, there's a lot more paths for these electrons to travel through, right?
Yeah.
So that's why resistance is inversely proportional to area. And now by extension, if you have two resistors in series and you add them, right, you get the equivalent of a longer resistor, right?
Hmm.
And the longer resistor means what happens to the overall resistance.
It would increase.
Yep. So that's why the equation is just, the sum of the resistors. Alternatively, if I had them in parallel, you're doing the equivalent of making a wider or, yeah, a resistor with a larger area. And that reduces resistance, which is why if this is R1 and R2 and you add them, it's a reciprocal sum. And a reciprocal sum must be smaller than either of the components of that sum.
Okay.
Right. Now, capacitors are the opposite. Capacitors are larger, are proportional to area and inversely proportional to the distance between the capacitors. So that's why if you added capacitors in series, you're essentially increasing the distance between them. So your overall capacitance decreases. So that's why capacitors in series will have the reciprocal sum,
Hmm.
whereas capacitors in parallel would have the equivalent of a larger area, which would mean you'd have a larger capacitance. So that's why capacitors in parallel, you add them up normally, right?
Got it.
Okay, now resistivity is this rho value, and that is intrinsic to the type of material that you're using. And conductivity is just the inverse of resistivity,
Okay.
right? So now we're being asked to figure out what information about an axon is required to calculate the current associated with an NCV pulse. So, I mean, if we have conductivity, we could figure out resistivity, which could give us this. And if we have length, that can give us this, but we still don't have area, so we can't find resistance. And if we don't have resistance, we and we don't have voltage, right? We don't
Yeah.
have what we need for V equals IR, right?
Hmm.
That's out. And then this one, potential, includes voltage. And then we have conductivity, which can tell us about resistivity, and we have radius. Now, the radius can help us learn about the area, and the conductivity can help us learn about the resistivity, and the voltage, of course, helps us figure out the voltage. But we would need to know the resistance, and we're missing the length of the resistor here.
Yeah.
Yep. And then C,
Okay.
yep. And then C is the potential, so voltage, resistivity, and radius. But what are we missing here?
The length.
Good. And
So,
then D, potential, resistance per unit length, and length. So we have the V, and then resistance per
yeah.
length, yeah, multiply.
Yeah,
Yep.
that makes sense. I think with this one, like n now understanding like what potential means,
Yeah.
because I was on the right track and I was like, well, we're still missing voltage. So I just
Got it.
assumed
Got it. Got
that
it.
that was the missing piece. But,
Got it. Okay. Yep.
Okay. Um,
Reducing sugars, I see something about.
yeah, I was not sure exactly. I know what a reducing sugar is, but structures still are giving me an issue. Like just visualizing things has been a recurring problem for me.
Got it.
Um, Trying to find that question.
Uh-huh. Got it. So, um, so yeah, what I was saying earlier about knowing the functional groups for the different types of biomolecular bonds, like a peptide bond is an amide bond and stuff. So, for instance, for a sugar, and this also ties to the biochem redox pathway that we went over, right? Or no? Like the generic kind of like if you oxidize like an alcohol, it would turn into something.
We didn't go over that, but if you oxidize an alcohol, then it would turn into a ketone or an aldehyde, depending on what kind of alcohol it is.
Okay.
And
And
then further, it could be oxidized to a carboxylic acid.
okay. All right. So so yeah, so this is a I think it's Tollin's test or something. So um both Tollin's test and Benedict's test, I think, test for reducing sugars. Now, if we have a sugar, like a regular, like, let's say, like glucose or whatever, like this, um, at this one carbon, you could have an OH and then an H here. So I'll use purple. So this oops, is this functional group. So I'll draw it here. That, right?
Mhm.
Does this ring a bell?
Um, Hemiacetal,
Yeah,
maybe?
yeah. And if this was another R, it would be
Hemiketal.
good. So these are going to be the functional groups of like sugars of like let's say like either a monomer or a monosaccharide, or if it's part of a polysaccharide, it'll be the one all the way at the end.
Mhm.
Now, is this something that can be reduced? Oh, sorry. Is this something that can be oxidized?
Um, yes.
Okay.
Uh, yes, I think
Yeah. Yeah. So,
because the alcohol can become a double bond.
yep. So,
Mhm.
yeah. So tertiary alcohols can't be oxidized further. Secondary could be oxidized to ketones, but the ketones cannot be oxidized further. And primary can be oxidized into aldehydes, which can be oxidized further to carboxylic acid and carbon dioxide. So
Mhm.
that's our, yeah, hemiacetal or hemiketal group that's just ever present on a monosaccharide. And now if we had another one of these, and I'm really not drawing like the rest of the OHs here.
Mhm.
Yeah, say we had, an OH here, and these bind um, through what type of reactions?
Glycosidic bond.
So, I mean,
Oh, like the type of reaction
yeah,
would be like uh mm,
it'll be like, what if you're really, really thirsty?
like a hydrolysis or dehydration reaction.
So, which one?
Dehydration
But is that,
because the OH would leave
oh,
with the other H.
that, right?
Yeah.
Good. But also dehydration synthesis, right? The synthesis part means you're combining, whereas lysis, you're splitting, you're breaking,
Hmm.
right? So then this would form this, where the functional group is this, right?
Hmm.
What could this be called?
Um, an acetyl group, is it?
When you say acetyl, you mean like acetal,
Yeah.
just because there's also,
Oh yeah. I
so
guess acetal.
good, good. And so that's a glycosidic bond. You're going to have an acetal. Now, can this be oxidized?
Um, no, no.
Correct. So you're going to have, so your reducing sugars will be like a monosaccharide, or if it is going to be a polysaccharide, um, only the last carbon, or sorry, the last monomer here would still have a hemi functional group.
Hmm.
So for but for within like, the polysaccharide bonds, like glycosidic bonds, they are not oxidized. It cannot be capable of being oxidized,
Got it. So
right?
then for the answer choices,
Mhm.
um it the let's see, the reaction will not result in the shiny mirror
Oh yeah, so
or
that comes from like the Ag like plus that would, if it turns into the shiny mirror, would be Ag solid, right? So it's
mhm,
gaining electrons, hence the reducing sugar, it reduces it. Um, and if it was Benedict's reagent, it would be like copper ion that gets reduced to copper solid, and that would give you a brick red precipitate.
okay.
Continue with what you're saying.
So D would be correct because they're like
Mm,
the anomeric carbon has another carbon attached to it
yep.
rather than an oxygen.
Yeah. So what we're looking for is, so in A, we have our acetal, like, glycosidic bond, which is never going to be reducing. But we do have the end of it, right? Be a hemiacetal, same thing here, but not here.
Okay.
So, yep.
Okay. Um, I guess one of the ones that I wanted to go through that I got wrong on the blind review was this one, which I understand now a little bit better, but I think um, fluids I'm still kind of having trouble with,
Got it?
especially in the context of the passage itself. Like, I think I just had an issue with determining what is like ambient pressure versus what is inside the burette.
Got it. Let's see. So, um, piece of magnesium ribbon was wound up and suspended in the open end of a 50 ml burette. The burette was then inverted into a beaker containing 100 mLs of water. Vacuum was used to suck the air out of the tip of the burette, filling it with water from the beaker. Air was then allowed in through the tip of the burette until the water level reached the decreased. Wait, okay, decreased to the 50 ml mark, which is the highest mark on the burette. And then 100 mLs of 6 molar hydrochloric acid was added to the beaker. After the magnesium ribbon was completely reacted in this reaction up here, which creates hydrogen gas, um, the water level was red, and the difference between the two readings was the volume of the hydrogen gas produced. Okay, now suppose that at the end of reaction one, the level of aqueous solution were 26 centimeters higher inside of the burette than outside. Okay, so let's see. This should be the 26 centimeters, okay, compared to the ambient pressure. The pressure of the gas inside the burette would be lower, the same, 2 times greater, 26 times greater. Okay, let's see. So, um,
The reason why I chose 26 times greater was because I was thinking of like the equation like density times GH.
uh-huh,
And so like if the height increased by 26,
uh-huh,
it would increase the overall, but like I think that was the wrong application of the equation.
got it.
Um, but that was my thought process. And I kind of figured it would be wrong because it seemed like a wrong answer,
Yeah.
but I picked it anyways.
Uh-huh. Okay. Let's see. So, okay. So if we had, so we have, okay. So they said in the passage that air was allowed in through the tip of the burette until the water level decreased to the 50 ml mark, the highest mark on the burette. So we have this air pressure, I guess, pushing down um, inside of the burette. And let's see. And then yeah, the ambient pressure is just it's essentially like the atmospheric pressure here pressing down against the like the the beaker that contains the water. So let's see. Um uh Wait.
I guess I was confused as to where the gas inside the burette was coming from, like what that even was.
Yeah,
Um,
so we have our magnesium strip here, and that's where we can do this reaction to produce hydrogen gas, which would bubble up here and, up here, and then that can
mhm.
push down against this fluid,
Okay.
right?
Yeah,
So,
I was having major trouble depicting what was happening in my head.
got it.
Um, so I guess in addition to like this question specifically, also like strategies for trying to
Got
piece
it.
this
Got it.
together.
Okay. So we are given a, oops. Um, okay. So so let's see. So if we have, let's say, yeah, this is our ambient or atmospheric pressure, and the that pushes down on this fluid in the beaker, which should cause the fluid in the burette to be pushed upwards. Like, does that part make sense? Like,
Yeah. Um, I guess also what what kind of equations would come to mind when you're looking at something like this?
got it. So, uh, since we have like, an atmospheric pressure and a hydrostatic pressure, it's going to likely be this one with the rho GH term indicating like,
Hmm.
the pressure of the water like column.
So that height there would reference the height of the water inside the burette.
Mhm.
And would that be like, would they have to tell you from what point you're measuring from? Or I guess because in this scenario, it's like, would it be the height from like the top of the liquid in the like the liquid of the beaker?
Yeah, so for instance, let's say that we called um the this down here is the pressure of, let's say, the air. So um the larger the like the ambient or atmospheric pressure, it should cause, so if the atmospheric pressure is larger than the pressure of air that pushes down against the water level here, so the water level would rise up if that's greater, like if PATM is larger than
So
the air. Yep.
then, like in this question, when it says that the solution was 26 centimeters higher inside the burette, that's like um this little part like here, um like between the top of the beaker fluid and then where the air starts, it would be like that little section. And
Uh,
if it's saying that it's higher, then the atmospheric pressure would be um greater.
yeah, so let's start with, let's say, when they are equal. So let's say
Hmm.
PATM is equal to P of the air inside, um, which would also include the water like column. So like, yeah, so let's say that if the PATM is equal to the pressure of the air inside of the burette plus rho GH, you could have, yeah, you could have that. Let's say like this is some type of height at which the sum of this rho GH and the sum of the pressure of the air pushing down this way would be equal to the atmospheric pressure here, right?
Okay.
And
Yeah.
for this one on the left, if the PATM is greater than the P air inside of the burette, then it's going to cause the, or I could say, then the PATM is going to be the P air plus that column of water.
Hmm.
And then if we had like an even like lower level, right? We could say that um lower level where a lower level of water that is, um higher value of air pressure, like the pressure of the air pushing down.
So then in that case, like would the line for where the air stops, wouldn't that be like below the beaker line?
So
Like if the pressure is greater?
sorry, you said below the air pressure below the beaker line?
Like the line of the air pressure would be below the fluid in the beaker. Is that what it would look like?
Um see.
because then the pressure of the air is pushing down more than the atmospheric pressure is pushing.
I see what you're saying. So, okay, if this was larger than this, um, then I guess, yeah, you would see that it's lower. Um, so, okay, so for this question, they're telling us that they ended up with the level of the aqueous solution inside of the burette was 26 centimeters higher inside of the burette than outside, right? So that means
Hmm.
that, so the main thing here really is just that, um, I'll use blue, is if I push down on this with like pressure, I'm pushing the water inside of the burette up.
Hmm.
And if I'm doing that, the pressure of the air inside of the burette decreases, right?
Yeah.
And if the pressure of the air inside of the burette like increases and pushes it down, pushes this level of water inside of the burette down, that would be when it would be larger than this atmospheric pressure, right?
Hmm.
That's just the general like conceptual idea here. So if they're telling us that the water level inside of the burette is 26 centimeters higher than outside of the burette, it means that your atmospheric pressure or ambient pressure, right, is larger than the pressure of the air inside of the, or the gas inside of the burette. Okay.
Got it.
So if they were like the same level, like they could be equal, but otherwise it's going to be that kind of like an inverse proportion. So,
Okay.
yep. So basically, your if the gas, yeah, if the level of the water is higher on the inside of the burette, it means that the ambient pressure is going to be larger than the burette. So this one would be compared to ambient pressure, the pressure of the gas inside the burette would be, yeah, should be lower.
Well, okay. Um, I don't think I had issues with like the rest of um
Let's see, wrong, untimed. Um, so the one with, okay, oxidation states change in a reaction, it'll be redox. Um,
mhm.
Perhaps add to that that um like you're gonna have both reduction and oxidation. And then let's see. Okay.
Yeah, that one took me a long time.
Oh, which one?
Like the redox one took me a long time.
Oh yeah.
I don't know if that was like a passage I was reading.
Seems like it was right before number 22.
Yeah.
Reaction one. Okay.
Oh,
Yep.
okay. I think I was unsure because first I was trying to weed out the fact that it wasn't double replacement
Okay.
and it would just be single replacement. And then uh Lewis acid, Lewis base, I was trying to weed out um because we had an acid and this Lewis acid accepts electrons. Um, so then I was like trying to figure out if it was accepting electrons or not. And then finally, I chose oxidation reduction
Got
because I did the oxidative states. But like I don't know, it just took me like a really long time, and I'm not sure like if there's a better way to go about this question.
Yeah. So first of all, whenever you see a reaction like this, you want to be aware of like, okay, what's happening and stuff. And
Hmm.
a lot of times, if you see a pure substance like these two, right?
Hmm.
Um, you can see that. So a pure substance must have an oxidation state of zero, right?
Yeah.
But when it is within a compound, it cannot have an oxidation state of zero, right?
Hmm.
So first, if you see these pure substances, think about that. Now, you mentioned Lewis acids and Lewis bases and Lewis acids as accepting electrons.
Yeah.
So now, if reduction reaction in redox is also accepting electrons, what distinguishes one from the other?
Um, like the oxidation state actually changes in redox.
So when it comes to, so let's say reduction, gain of electrons, Lewis acid, gain of electrons, except Lewis acid isn't just gaining electrons, it's gaining an atom of something else. Because a Lewis
Okay.
acid is an electrophile, like this,
Hmm.
and let's say this is a Lewis base. So sure, the Lewis base has a lone pair that it can donate to this electrophile, this Lewis acid, but it's not just giving away electrons, it's also binding to it, right?
Okay.
So so like I understand that you're thinking, okay, Lewis acid gaining electrons, reduction gaining electrons, but in reduction, you're gaining electrons simply. Like that's it. Lewis acid, you're gaining electrons through gaining a whole other, bond to an atom.
So then I guess I still wasn't sure because like there is a replacement going on, so technically one could be gaining electrons through like gaining
So now
something else.
the same reason that I circled these um would also explain why it wouldn't be a double replacement because we have two pure substances, right? If it was a
Yeah.
double replacement, you would see like you wouldn't see these. You would see something like um what kind of example can I think of? Like I don't know, like HCl plus like NaOH can yield like H3O plus OH minus, something like that, where like the H can attach to the OH to get this, and then, well, I guess I didn't have the OH attached to the other thing. But sorry. But yeah, in a rep, double replacement or whatever, you're gonna see like two things um get switched.
Hmm.
Yeah, let me see a good example of this. So, um, yeah, so I guess it could be um, like, oops,
I guess so. Like I was able to. like it took a while, but I was able to figure out that it wasn't double replacement, but with like Lewis acid, I guess. I was still confused because even in like our definition of that, like that the electrons are moving with another um atom, it's like the HCl is turning into MgCl2. So what isn't it like still moving with an atom?
So here I just drew an example of a double um replacement.
Hmm.
You can see that you're not, so the barium chloride, the barium and the magnesium sulfate, the barium portion and the sulfate portion combine here, and the magnesium and chloride formation combine here. So you're not, so in a double replacement, you're not ever going to get like a single Mg or a single H2.
But like in the Lewis acid, Lewis base,
Oh yeah.
couldn't
Yeah, what about
couldn't it be a Lewis like couldn't it still be a Lewis acid because the HCl is turning into MgCl2, so it's gaining another atom of sorts.
uh well, this is more so that so sure, this is like a single replacement, right? But if you just think about this H, but in HCl, this H has a +1 charge, and then in
Mhm.
H2, it's a 0 oxidation state, and then Mg solid is a 0 oxidation state, and MgCl2, it's a 2 plus oxidation state. So you're not adding uh you're not adding bonds to uh these elements here.
So you're not looking at the chlorine, like the chlorine's oxidation state would be -1,
Hmm.
and then it changes to -2 with the addition of magnesium.
Well,
Like that's kind of what I was looking at.
it still stays the same. That's why there's two chlorines, right? Like HCl, H is +1, Cl is -1, MgCl2, Mg is 2 plus. Cl is still -1, but since there's two of them, right, this will give you -2. But the chloride ion is still having an oxidation state that is not changing. You just have two of them there.
Oh,
Mhm.
okay.
Yeah. So Lewis acid, Lewis base, a good example of that would be like let's say like ROH plus COO, or like, oh, like an aldehyde should give you a carboxylic acid, right? Because we have, let's say this is our CHO and then this is our ROH. It attaches to this to give you, the O minus, the H, the uh whoops, the HOR, and then this comes back, kicks off a leaving group to give you your carboxylic acid like that, right?
Okay.
But because a Lewis, so Lewis definition is relevant for nucleophilic and electrophilic stuff. So if you think about that, that means that you're adding like molecules or adding atoms and stuff. So if you're donating electrons as well as atoms, that'll be Lewis acid, Lewis base, like nucleophile, electrophile, orgo stuff. But
Hmm.
oxid like redox, you're simply either accepting or losing electrons, but without the atoms being changed.
Okay. Okay.
So clues for that are if you see a pure kind of substance like Mg, solid, charged oxidation state must be zero, H2, gas,
Mm-hmm.
stuff like that.
Okay. So I guess if there's a pure substance in a reaction, like chances are it's going to be redox.
Yeah, like, well, because a lot of times you'll have, so I would just say that if you have a version, if you have your pure substance version and you have a version of it that is charged and that changes, then yeah, that would be redox.
Okay.
You have to have the other thing. Like in order for reduction, you have to have the oxidation. Yeah.
Okay. Um,
Ultrasound machine is not moving, therefore we do not need the speed of the observer.
yeah. Um, that one was kind of just like a
Hmm.
not like I don't know what I was thinking on my part.
Hmm.
But it was just about the Doppler equation. And I like assumed that there were five variables in the equation, but because the machine is not moving, there's actually four variables. So
Hmm.
I think that's why it took me so long.
Hmm.
This one I think might be an issue with comprehension. Yeah. This one, I for the question, I thought it was like a pseudo discrete where it was saying like if you add metal ions, like metal ions can be cofactors, so it would increase the amount of binding. Like that was my thought process, but in reality, it was saying to go to the passage. So I guess I was having some trouble understanding the passage, maybe.
Yeah, okay. Let's see. When studying new drug candidates, it's important to understand how they interact with plasma proteins as drug delivery to tissues is facilitated by the plasma. So serum albumin is the most prominent protein in the plasma, and it contains several binding sites that can accommodate a structurally diverse set of ligands. Um, Although diverse, the ligands tend to be mainly hydrophobic with anionic or electronegative features, and many commonly used pharmaceuticals fall within this category. Um, Therefore, binding affinity to SA is a main factor in determining the bioavailability of a drug. A study was conducted to understand the interactions between a drug called CPFX, figure 1, and BSA. So we have the structures here, and we want to just spend a little bit of like a couple of seconds identifying functional groups. What functional groups do you identify here for each of these?
I see carboxylic acid, carbonyl group. There's um a ring structure, well, multiple ring structures, alcohol.
Mhm.
Um,
Okay, cool. And we kind of see something. Oh, what's this functional group called?
um, an ester.
Yep, and if it's a cyclical ester, it's called a lactone.
Oh, right.
Huh?
Okay.
Good. And ibuprofen. All right, cool. So all right, the binding constant of CPFX to BSA was determined using spectroscopic techniques. In addition, so in general, what do they mean when they say spectroscopic?
Um, like IR spec
So,
or just different kinds of techniques to analyze properties of the molecules.
so would chromatography be one?
Um, I mean, by the definition I just gave, yeah,
But
but maybe not.
so spec means light.
Oh, okay.
So it would be like, so chromatography would not be one, but it would be like, um, like IR, NMR, UV is, you know, stuff
Okay.
that happens, stuff that has to do with light. Okay. Um, in addition, known BSA binders, warfarin and ibuprofen, were used to determine the specific binding site of CPFX. So if they're known binders to BSA, what could this be called in an experimental design context?
The controls,
What type?
positive.
Good. Because we know that we're going to get a result, right? Positive result.
Hmm.
Okay. Now, they bind specifically to they bind to separate sites, one and two respectively. So that means warfarin binds to site one, ibuprofen binds to site two, right?
Hmm.
Okay. And table one, BSA, CPFX, binding experiments in the presence of warfarin and ibuprofen. Note K naught represents the affinity constant of CPFX in the presence of BSA only. What is that saying?
Um, like the affinity for um CPFX when BSA is present, but not when the um like when warfarin and ibuprofen were used, which um also bind to BSA.
So in the Ka column, we see like essentially the affinity for like first warfarin binding to BSA and then ibuprofen binding to BSA. Um, and what do we kind of see here?
Um, well, in the column on the right, when it's saying that the association is in the numerator with
Oh, before
like
that, just here.
no, on the right side.
Yeah, but before that, just what do you see here?
Oh. Um, the ibuprofen has a larger Ka,
Yeah, it's
which
like
means
double, right?
it's yeah.
Okay,
So that
cool.
that means that it has a like it won't dissociate as much.
Mhm.
Like it just has a higher affinity for the enzyme.
Exactly. Okay. And then now the second, yeah, column, or sorry, the column on the right.
Um, that has the Ka in the numerator, and then in the denominator is without the protein or the binder.
Okay.
So if it's greater than one, that means the affinity of the warfarin or ibuprofen is higher than the normal affinity. And then if it's lower than one, it has a smaller affinity than um, just with BSA.
Mhm.
And I think that was something I missed in
Uh-huh.
the question. Um,
Because
I
both,
don't,
yeah, go on.
I don't know if I missed it because I didn't read the table description or like if it was because I just didn't like understand what like why that was even there in the first place.
Mhm.
But there was definitely like some sort of comprehension error there.
Got it. So when you see these tables, make sure you read the captions because that will be very important. And now the Ka over K naught, we see the values are less than 1, so we know that the K naught is larger.
Hmm.
And if the K naught's larger, what does that mean exactly?
It means that whatever the Ka represents, like if it's the affinity for like warfarin,
Okay.
then the warfarin binds not as well, I guess, as just the CPFX and BSA together.
Yeah, so so the CPFX's affinity to BSA is larger than its affinity to CPFX's affinity to BSA in the um in the presence of warfarin, right?
Hmm.
So, and we see the value is larger for ibuprofen, which would mean that, what would that mean?
It would mean that I guess the enzyme prefers to bind with ibuprofen than warfarin, or like the site marker, I guess, like it prefers to bind in site one because ibuprofen is taking up site two.
Okay. So, uh, so K Ka over K naught could be like inversely proportional to K naught or proportional to Ka, and we see a larger value for ibuprofen. So either we have a smaller K naught or a higher Ka or both. But we do know from the middle column that ibuprofen has a higher Ka. So that could, play a role. And it seems like the Ka over K naught. Um, Actually, K naught is the same for both, right? Because it's just CPFX
Yeah.
to BSA. So the only thing that's changing is the Ka. And it makes sense because the Ka for ibuprofen is double.
Hmm.
So the Ka over K naught is roughly doubled as well, right?
Yeah.
So yeah. So like, I know on the test, speed, time crunch and all that. Um, so maybe, but yeah, I would just say like when you're reading it for the first time, spend just a couple of like, I would say like 10-15 seconds trying to look at the table and kind of gather your insights for it. So
Okay.
so like what I would see here is just, two times difference here, two times difference here. So, okay. Then let's see. Analysis of the data showed that electrostatics were important to CPFX binding. Um, so what's that essentially saying?
Um, well, electrostatics, like the charges of the molecules
Mhm.
affect the binding.
Good. Okay. Additionally, the effects of metal ions and temperature on this binding were investigated. All right, and then table two, binding in the presence of metal ions. K naught is in the absence of the metal ion. So we see these various Ka terms that are all, roughly similar numbers. Then Ka over K naught seems to be slightly different. We could see that K, well, first of all, we know K naught is larger because all these values are less than 1. And yeah, and basically we have that. And then at the end, table 3, thermodynamic parameters at a pH of 7.4. ND means not determined, so 298 Kelvin, Ka of this. Um, various values that they could ask us about in order to find like, delta G and stuff. So okay,
Mhm.
had the solution here. All right. So, what are your thoughts here?
Well, again, like going back to what I was thinking, I thought it was a pseudo discrete. So I was just thinking about like my knowledge of metal ions with binding affinity. Um, and
Question.
I,
So
hmm?
for these passages, do you read the questions first or what?
No, like beforehand, no.
Okay.
Should I be? Okay.
Because
I,
I asked was because when you were doing this, you were treating it as a discrete, pseudo discrete or whatever. But so I was asking that
I
because
mean, I think I was treating it as a pseudo discrete because when I went back to look at the table, I didn't really know what to do with it. So I thought that because like I was looking at the Ka values
Mhm.
with Mg2 plus, and then like I was seeing that they were kind of like the same or like similar like with all of them. So I didn't really know what to do with that. And that was because I didn't understand the Ka over K naught value, I think.
so
So
perhaps
then I thought it was a discrete because I didn't know what I was doing.
so you're saying that this is uh that you perhaps you didn't read the caption.
Yeah, I think I skipped over the caption, or if I did read it, I didn't understand like what that would mean in the context of like a question like this.
Got it. So yeah, so always read the caption and always, especially when you're evaluating tables, know what the you know what the columns stand for. So so yeah, Ka you understood, but the Ka over K naught, um, you want to make sure you understand. And because that so oftentimes ratios and things will give you a lot more information than just Ka. And so now if you look at these choices, right, we see like metal ions present in plasma. So did you go to like table two?
I went to table two. I didn't really understand it.
Okay,
And so then I just based it off of my knowledge that like a metal ion would probably increase binding.
I see. Got it. So okay. Yeah, so like what you would have done here is metal ions are expected to, and we see the choices are talking about like amount of the CPFX bound to BSA for the most part. And so if we look at table two, we could see that the Ka values are values in the presence of metal, right? But
Hmm.
if the question's asking what does the presence of metal ions do, we would need to compare it to when it is without metal ions, right?
Yeah.
So that's where the K naught part comes in. And since the Ka over K naught values are smaller than 1, it means that the K naught is larger than Ka, which means that the binding in the absence of metal ions um are is better, right?
Hmm.
So that should lead you then to, um B, right?
Yeah.
So yeah. So I guess takeaway here, make sure you read the caption and make sure you understand yeah, like what the values in the table mean
Hmm.
and pay particular attention to ratios.
Okay.
Ratios are very useful because they tell you like, well, first of all, it a ratio will contain two pieces of information, and that's always better than one. Like Ka is one piece of information. And two, ratios that you look at intrinsic, sorry, intensive properties.
Okay. Yeah, I think like that's part of my problem with tables because I have noticed I mean figures are difficult, but like tables I actually find more challenging just because I see like all of the numbers and like it takes me longer to interpret them.
Got it, got it. Could be a lot. Yeah. So, um, got it. So yeah, pretty much like yeah, for these tables at least, like, you so when it comes to ratios, you want to be thinking, and you were saying this earlier, like there's really three kind of possibilities for a ratio. Either, the top number and the bottom number are equal, in which case the ratio is one. Top number larger than bottom number, the ratio is greater than one. Top number smaller than the bottom number, ratio is less than one.
Hmm.
Whenever you see some column like this, that's a ratio. When I say ratio, I mean, divide like a quotient of some sort. Um, you want to be checking, like it's less so about, whatever the values are, and more so about, is this less than one, equal to one, greater than one, stuff like
Okay.
that.
Okay. I guess that'll be like helpful for my next table analysis. So,
Yep, yep. So let's see. Wrong, untimed, MC delta T equals Q u usage.
yeah, I just have I have to keep working on like specific heat and heat capacity equations. I think I'm gonna do like a couple more practice problems for those.
Uh-huh.
But
Like a math problem, because I also want to see, like, how you do the math stuff. Um, I mean, like, yeah, if you think
I
that.
didn't hear the last part of what you said.
Oh yeah,
Sorry.
so I was wondering if that was 36 was like a math problem, and I'm curious about how you would approach
Um,
a math problem.
no, it wasn't it was a math problem, but I didn't have
Hmm.
an issue like doing the math. It was like picking up that I should have used that equation.
Okay,
I think I'm just still kind of having like some issues determining when that equation gets used.
got it.
Um, yeah.
So would you say that happens somewhat often for formulas, like if you're not sure which one?
Yeah.
Okay.
It's getting better. But like specifically with heat capacity and specific heat, like those, I tend to not be able to pick up that I should be using that. Because I think there was another question in this test where I didn't use it either, and I should have. And then I have noticed that I've done that before. So,
Yeah, okay. If you want, you could show it to me.
mm,
What is the minimum amount of heat energy required to increase temperature from 373 Kelvin to 573 Kelvin, and the specific heat capacity of iron is 460. So, okay. So, like any calculation problem, start by taking an inventory of what you're given. So we're given two temperatures, which would be delta T.
mhm,
Specific heat is little c, and they're asking about heat energy, which is Q, right?
Yeah.
So you would then think what equation would have Q, little c, and delta T?
Yeah, I think I didn't um realize that heat energy was Q, so maybe that was a problem. Like the way I went about solving this was uh just using like the units from specific heat capacity and like trying to cancel out the units, and it got kind of messy. Um
Uh-huh.
and I think I was like starting to run out of time too, so I was getting overwhelmed.
Got it. So like the Q, like, you don't necessarily have to remember like the Q, like that it's called, that we can call it Q. But from the units, right, we see that specific heat capacity. So they're asking for heat energy, which is going to have a unit of what?
Joules.
Joules, right? So, and they're giving us specific heat, which is joules over kilograms times Kelvin. And they're giving us the delta T, which is in Kelvin. So the Kelvins cancel. And then you just need to get rid of the kilograms in the denominator by multiplying it by some mass, right?
Yeah.
And so, yep, that's what you would do. So it doesn't even matter if, you remember whether something, a formula has capital Q or not. From the units, you can figure it out that way, right?
Yeah, I think because I was figuring it out that way, but then I was not sure what to do with the temperature because at that point I didn't know it was like delta T. So I like for one of them I solved with the 373 and then a different one was 573 and it just got like really messy. Um and yeah.
Got it. So since they're asking, so if they asked, what is the heat energy, you know, at 373 Kelvin, that would be something like that. But they're asking, what is the heat energy required to increase temperature from this to this,
Hmm.
right? Because, if you think about it conceptually, like heat energy is the energy of heat, so it contributes to increasing the temperature. So, so there's that, and then also just them asking what's the amount of heat energy needed to increase a temperature shows that, we're going to be raising, uh, or we're going to have a change in temperature.
Hmm.
So,
Okay. Okay. Yeah, I guess I'll like try and do some more practice problems with those. Like maybe the ones with Jack Weston. But um okay. Yeah, I think like for now that's probably pretty good. I can't really stay past 5:30-ish anyways because I have to go soon.
oh,
Um
for sure. So,
um
uh,
but I guess like for next week I'm taking the next full length on Tuesday and then our session is like right after that.
mhm.
So I guess we could maybe go through like a couple questions from that practice exam. But just at that point, I wouldn't have gone through any blind review or anything because I would have been fresh, like out of the test
So you're saying, let's see, when we're meeting on,
on the 18th, I think.
on Tuesday, that
Yeah.
that you would want to go over what?
I mean, if you think it would be helpful to go over questions from that test, because I wouldn't have seen them yet again, because I wouldn't have done the blind review.
Got it. So the next test you're taking is AMC 2 or free exam?
Um, taking the the free scored one.
Oh, got it. Okay. Now, yeah, we can do that. But yeah, I just really want to make sure that you like I guess today we didn't really go over like specific calculations and stuff. So yeah, I was just trying to see from the rest of the stuff that you wrote, like number 46, the Archimedes thing with W air minus W water.
Yeah, that one,
Mhm.
uh, I like just had some problems understanding like what the weight of air minus the weight of water would be. So I'll probably need to do some more practice problems surrounding density specifically, I think.
Yeah, and buoyant force.
Yeah,
So
yeah.
but yeah, I really want to dial this CP section in. So I really want to make sure that like, that the way that you're like if it's math stuff, like the way that you're doing the math, like if that's like consistent and then the formulas that come to mind and stuff, like in addition.
Hmm.
I'm also seeing things where it's like this whoops didn't put two and two together. They gave us voltage, didn't know to use E is equal to Q times V.
Yeah, that was like that was
Mhm.
equation one where I didn't pull the right equation.
Uh-huh. And then I see one with another one that's MC delta T.
Yeah, but by that point, I wasn't even really able to answer the question at all
Got
because
it.
I was running out of time.
Got it. Yeah, times zero. So, okay. So, um, I would say like, yeah, see if you can find these types of patterns and the questions that I sent you before, like those two like physics questions, like were you able to
I
do?
was able to do them, but it took me a really long time.
Yeah.
Um, because I was having trouble like reasoning out what I should even start with.
Uh-huh.
Um,
Yep. Got it.
yeah.
So yeah, sometime like yeah, I guess next time like if we have some time, I want to just go over like a question like that, just to kind of hear you like reason it out. And in the meantime, I would say, when you're doing your Anki, like you know, you were using like the miles down deck or
I've been
Jack Sparrow.
I use the miles down for the essential equations,
Yeah,
but then for the rest of the time that I'm using Anki, I go to like the test mistakes that I made and I'm like using my own cards
got it.
from like UWorld and the full lengths, stuff like that.
Got it. So now with the equations, do you, because I'm thinking about like how like you didn't think of like the Q equals MCAT kind of equation. So I'm thinking,
Yeah.
how are you with the equations and the units and stuff? Like, do you
Um,
have,
I
yep.
the equations are getting better, but I think it's like pulling them when I need to because like for miles down, for example, it's just asking like what is the equation for this?
Mhm.
It's not putting it into context, and I think that's where I have a problem with it.
Got it. So I would say for those equations, the ones that, I mean, so typically when you do a calculation problem, you start off by taking an inventory of what you have, and then you can see like that question that we saw with heat required. So we know we're trying to find heat, temperature increase from this to this. So that constitutes delta T. And the specific heat is this. So there's a C. So there's, you can combine uh, the values that they give you to figure out
Hmm.
what unit to use. So, maybe like next time we could also spend a couple of minutes just kind of going over equations and like in addition to like just memorizing the equation, like what context would this be used and
Yeah.
what these values are representing. So,
Yeah, I think that would be really helpful.
okay. but in context of just the calculations themselves, how are those? Like, do you,
Um, I they're okay. I, uh, they're okay.
yeah,
The rounding is okay. It's unit conversions still. I'm definitely better than I was with the unit conversions. But it's still a work in progress, I think.
okay. So that's something that, yeah, we'll work on as well.
Yeah.
So, but yeah, I really want to dial these things in by the time you take your next test. So yeah, maybe I'll send some like problems or passages and stuff. And all right then. Awesome. So I will see you on Tuesday the 18th at 4:45 Eastern. And oh, and then yeah, we kind of ended up doing like the 2 hours anyway, so
Yeah.
150 and